Hello friends, in the previous class we have derived an expression for electric field at a point due to uniformly charged infinite long conductor and was found to equal E equal to lambda upon 2 pi epsilon naught into R. It is for uniformly charged infinite long conductor, and today we shall derive an expression for electric field due to uniformly charged infinite plane sheet. And to obtain an expression for electric field, here we use Gauss theorem. If it is a point charge, then only we can use E equal to 1 upon 4 pi epsilon naught into Q upon R square. But here charge is uniformly distributed, that is, charge is continuous on the surface. In this case, we use the total charge on that surface in terms of charge density, that is surface charge density. And surface charge density is the amount of charge per unit area of the plate or plane surface. Thus, charge Q equal to sigma into A. And to find electric intensity due to uniformly charged plane sheet, we consider Gaussian surface, or we imagine a Gaussian surface. A Gaussian surface, it is a closed surface enclosed by a charge, is called Gaussian surface. And then we calculate flux through the surface, curved surfaces of cylinder and plane surfaces at point P1 and P2. Then compare the flux calculated by mathematics or theory and the flux according to Gauss law. Then we get electric intensity. Clear? So, consider an uniformly charged infinite, that is long, plane sheet. Let sigma be the charge density on this surface. If this surface is divided into small elements, then each element has a charge is equal to sigma A. Let P1 and P2 be the 2 points on the front side and back side of this plane sheet. They are at equidistant from the plane surface. Now, to calculate electric field at P1 and P2, imagine a Gaussian cylinder passing through these points. Let A be the surface area of plane surfaces of Gaussian cylinder, and this is curved surface of cylinder. And now we have to calculate or estimate the flux through curved surface, plane surface, first plane surface and second plane surface. Then we get total flux through the Gaussian surface. If phi1, phi2 and phi3 are the flux through curved surface and two plane surfaces, then phi1 is equal to Ea cos theta, where theta is the angle between field vector and area vector. For curved surface at any point, this area vector is always outward normal. Area vector is outward normal, and field vector, it is along the curved surface. Therefore, the angle between area vector and field vector is 90 degree. Therefore, if theta equal to 90, cos 90 equal to 0, hence phi 1 is equal to 0. That is, flux through curved surface is equal to 0. Now, phi 2 be the flux through the surface area A enclosing the point P. Then flux through this plane surface is, here area vector, it is perpendicular to the surface, outward perpendicular for closed surfaces, since cylinder is a closed surface. Therefore, both area vector and field vector and area vector are along the same line. Therefore, angle between field vector and area vector is 0. Therefore, flux through second surface phi 2 equal to E into A, since cos 0 equal to 1. And phi 3 be the flux through third plane surface. Here electric field is directed away from the charge because charge is positive, and area vector is also outward normal to the surface. Hence, the angle between area vector A and field vector E is 0. Hence, phi 3, that is flux through third surface, is E into A. Therefore, the total flux through the Gaussian cylinder is phi E equal to phi 1 plus phi 2 plus phi 3. But here phi 1 equal to 0 and phi 2 equal to EA, phi 3 is also equal to EA. Hence, phi E is equal to EA plus EA equal to 2EA. Consider this as equation 1. Now, according to Gauss law, electric flux through a closed surface is 1 upon epsilon naught times the net charge enclosed by it. Thus, phi equal to Q upon epsilon naught. Since here charge is uniformly distributed, therefore the charge, total charge, is given in terms of surface density. And according to the definition of surface density of charge, sigma equal to Q upon A. Therefore, Q equal to sigma into A. Thus, Q can be written as sigma into A, because sigma is equal to Q upon A, charge per unit area. Therefore, charge equal to surface density into area. Now, from equation 1 and 2, 2EA is equal to sigma A upon epsilon naught. Sigma A upon epsilon naught. Here A and A get cancelled. Therefore, E equal to sigma upon 2 epsilon naught. This is the expression for electric field near an uniformly charged infinite plane sheet, and it is independent of the distance of the point from the plane sheet. And next we shall derive an expression for electric field at a point due to uniformly charged spherical cell. Spherical cell or spherical sphere. The spheres are of two types, hollow sphere and solid sphere. You may take any one. In case of hollow sphere, if charge is placed at Q, according to properties of charge, charge always resides on the surface of the conductor. Therefore, this charge is uniformly distributed on the surface of spherical conductor or spherical cell. And in case of solid sphere, if charge is given or pierced inside the solid, since due to the conducting property, the charges conduct and they reside on the surface. Therefore, in case of conducting spheres or spherical cells, the charge is always resided on the surface of sphere or spherical cell. It may be hollow or solid. Now, consider a spherical cell or sphere with center O. Let Q be the charge placed at the center. But according to property of charge, it always resides on the surface. Therefore, this charge conducts and it is uniformly distributed on the surface. Uniformly distributed. And this is the spherical cell with O as the center. Let capital R be the radius of this spherical cell, or be the radius of spherical cell. Now, let P be a point at a distance small r. P be a point at distance r from the center of sphere. From the center of sphere. And in this case, we cannot use directly intensity E equal to 1 upon 4 pi epsilon naught into Q upon R square, because charge is uniformly distributed. In case of charge distribution, we use Gauss law to obtain electric intensity. To find the electric intensity at point P, we imagine a spherical Gaussian surface with center O. With center O, we draw a spherical sphere. This is Gaussian surface. Gaussian surface. Now, here the field vector is along the radius. This is also radius and is directed away from the charge. Therefore, field vector, it is radial outward, and since it is a curved surface, any straight line passing through the center, a straight line, it gives the direction of area vector. It gives the direction of area vector because the electric field intensities are in all directions radially, and field vectors also along the radius. They are also radial. Therefore, at each point of this Gaussian surface, electric field vector and area vector both are in the same direction. Both are in the same direction. Then flux through the point P. Consider a small element of area dA. Then flux through the point P is given by phi equal to E into summation of dl. dl is the length of small element. This element can be divided in smaller elements, symmetric smaller elements, and the sum of them dl is equal to length. And area of the sphere or spherical surface is A. If dA is the elemental area, then such dA all elements are added so that total area is A. Therefore, flux phi is equal to EA cos theta. But for a closed surface, curved surface, field vector and area vector are along the same directions at any point on the surface. Therefore, theta equal to 0, cos 0 equal to 1. Here E vector and A vector are parallel to each other. Hence, theta equal to 0, cos 0 equal to 1, hence phi equal to E into A. Where A is area of spherical surface. If small r is the radius of this imaginary spherical surface, Gaussian surface, then area of the sphere is E into 4 pi r square. E into 4 pi r square, where r is radius of Gaussian sphere. Now consider this as equation 1. This is the flux through the spherical surface, Gaussian spherical surface. Now applying Gauss law. According to Gauss law, total flux phi E, also phi E is equal to Q upon epsilon naught. Q upon epsilon naught. Consider this as equation 2. Now comparing equation 1 and 2, E is equal to E into 4 pi r square is equal to Q upon epsilon naught. Therefore, E is equal to 1 upon 4 pi epsilon naught into Q upon r square. Here r is distance of the point from the center of sphere. And this expression is similar to an electric field due to point charge. But here charge is uniformly distributed. When we observe this electric intensity from the outside, then the field lines appear to come from the center of the sphere. Therefore, we assume that the entire charge on the sphere seems to be concentrated at the center of mass of sphere. Hence, electric intensity at any point outside the sphere is E equal to 1 upon 4 pi epsilon naught into Q upon r square. And suppose if the point P lies inside the sphere, consider a sphere, I take a large sphere of radius r, and charge is uniformly distributed on the surface. And let P be a point at a distance small r from the surface. Then what is electric intensity at a point inside the sphere? According to Gauss law, Q upon epsilon naught. And to find electric flux using Gauss law, we draw a sphere with radius small r and is called Gaussian surface. Then what is the flux through this Gaussian surface? Here electric field is directed away. The direction of E and direction of A are in the same direction. Therefore, flux phi equal to, we can calculate as E into A. Here theta equal to 0, cos 0 equal to 1. And according to Gauss law, phi electric flux is equal to Q upon epsilon naught. Consider this as equation 2. Therefore, EA is equal to Q upon epsilon naught and E equal to Q upon A epsilon naught. But inside the sphere there is no charge. If Q equal to 0, E equal to 0. Therefore, electric intensity inside a charged sphere is 0 and outside the sphere is 1 upon 4 pi epsilon naught into Q upon R square, and here electric intensity due to uniformly charged sphere is inversely proportional to square of the distance. Clear? And in next class we solve numericals from NCERT book, that is exercise problems, and follow the NCERT book. Thank you.